Hello everyone, this is Dr. Indradeep Kumar, Assistant Professor, IARE, Hyderabad. So in this video, we will see problem on a structural loading. Okay, so topic we will cover is problem on a structural loading. So first we will see the theory how to find that problem, and then after that we will see the numericals in next video. So first let's see this one. First I am just recalling the previous concept also earlier also but because of this again we are recalling that one, so that easily you can understand the numericals or problems. So yes, yeah, the principle of the stationary value of the total, actually here total potential energy, right? So just yeah, the total complementary energy method. Okay, so the principle of the stationary value of the total complementary energy may then be stated as, so what is that? So here that for the total complementary energy statement is what? For an elastic body in equilibrium under the action of applied load. So just here, this is for what? Elastic body. That is what? In equilibrium. So elastic body in equilibrium under the action of applied forces, the true internal forces or stress and reactions are those for which the total complementary energy has a stationary value. So just here, the first thing was that body should be elastic. The next, that should be in equilibrium under the applied action load, right? Under the action of applied load means that body, after applying the load, that body also should be in equilibrium, right? The true internal forces or stress, how much they will experience the internal force or stresses, and reactions are those for which, right? For those for which the total complementary energy has a stationary value, right? So that complementary energy should have a stationary value. Okay, consider an elastic system in equilibrium supporting forces P1, P2, P3, so on, Pn, which produces real corresponding displacement at point 1, 2, 3, so on, as delta 1, delta 2, delta 3, delta 4, so on up to delta. Means because at P1, because of P1, delta 1 displacement at point 1, P2, delta 2 displacement at point 2, P3, delta 3, and so on. If we impose virtual forces delta P1, delta P2, so now P1, P2 is the what? That actual forces acting, right? Now what we are doing? We are for virtual forces. So virtual force, what we are giving that as delta P1, delta P2, delta P3, so on the system acting through the real displacement, right? So where the real displacement is that one, right? On the system acting through the real displacement, then the total virtual work done by the system is what? Minus integral of volume y dp plus sigma r equals to 1 to n del r plus dou p r. Okay, so see here, the first term in the above expression is the negative virtual work done. So this is what? Negative virtual work done because of what? By the particle in the elastic body. So inside the body, whatever the material is there, the elastic body is there. So whatever the particle of inside that body is there, that's why, because of like iron is there having different, aluminium will have different. So inside the whatever the particle is there, because of that particle this will be there, and that's why that is the negative virtual work. While the second term represents the virtual work of the externally applied virtual forces. So this term is when we applied because of the applied virtual forces, and this is because of the internal particles of that material or system, whatever is there. Okay, so this is because of the actual or externally applied virtual forces. Okay, from the principle of virtual done, the sum of energy should be equals to what? 0. So this plus this, just simply this is equals to 0 from the principle of conservation of energy or from the principle of virtual work. So from here what we can say, now just see here, comparing this equation with CE equation, that complementary energy equation, we see that each term represents an increment in complementary energy. The first of the internal forces, the second of the external load. So this is because of the internal force, and this is because of the external force or external load. Above equation may therefore be written as del equals to Ci plus C. So instead of this, the bigger, just written as Ci plus C del, that differential of this one, that is equals to 0, where Ci is what? Integral of volume 0 to P y dp, right? Plus C is what? Minus integral of r equals to 1 to and delta r pr. We shall now call the quantity Ci plus Ce, this quantity, the total complementary energy of the system. That total complementary energy C of the system. So this C is equals to sum of these two Ci plus Ce. Okay. Now application to the deflection problem. Let us suppose that we require to find the deflection at delta 2. Right. So now we are finding deflection at delta 2 because of load what? P2. In the simple pin joint framework consisting say of k members, suppose just a k member, that can be 5, 10, anything, right? In that, what we are doing, we are finding deflection at delta 2, right, because of load P2, okay, and supporting load P1, P2, P3, so on. So because of P2, delta 2 will be there, but other loads are also acting, right? From the above equation, the total complementary energy of the framework is given by C equals to I equals to 1 to K, 0 to Fi, where Fi is just here. Lambda I dFi minus R equals to 1 to N delta R PR. So here force is what? 0 to Fi, where what is I? Because how many members are there? Let's see, K members are there. So force acting on each member. So for first member, this will be 0 to F1. Second member 0 to F2, so third member 0 to F3, like that. One similarly deflection, and lambda is what? Displacement, right? Or deflection in that one. So 0 to F1, lambda 1 dF1. For second member 0 to F2, lambda 2 dF2. Third member 0 to F2, lambda 3 dF3. For K member 0 to Fk, lambda K dFk. So this is because of the force. Now this one, right? R equals to 1 to N delta R PR. Again similarly here R equals to 1, then delta 1 P1, R equals to 2, delta 2 P2, delta 3 P3, so on, delta PA, delta N PM. So this will be the total complementary energy method. By this we can see. So we will see the numericals based on this one in next video. Where Li is the extension of the ith member. Li for first member, for that means I equals to 1, Li will be what? L1. L1 will be the extension in first member. L2 will be the extension in second member. L3 extension in third member and all. Fi, the force in the ith member. This is what we have to do. First we have to find force in each member. Later I will show you. First you need to find force in each member, and then because of that force, what will be that extension in that member, F, because F, suppose force is acting in first member is F1, then because of F1, what will be the what will be the extension in first member, okay, and R, the corresponding displacement of the rth load PR. So because of P1, delta 1 will be the deflection, because of P2, delta 2 will be the deflection, right? So here according to this question, what we are finding? Delta 2 of P2. So here this we can remove, and this we can write delta 2 P2. This will be there, and this delta 2 P2. Yeah. So what we can write before this? C equals to sigma I equals to 1 to K integral 0 to Fi lambda I dFi minus delta 2 P2. Right? So P2 is what? Because of del P2. So just here. So this will be del P2 because that virtual force is acting. Right? So that is here. Now if we will differentiate this with respect to P2. So just we have to differentiate this with respect to P2. So after differentiating, what we will get here? Because what was the condition earlier? Apply, if load is not there at that point where we have to find the deflection, apply the fixed load and differentiate with respect to the fixed load. So here what we are doing, we are applying the virtual force, that delta P2, that is the fixed load, and then we are differentiating with respect to P2. So here this is our equation. Once we will differentiate this with respect to P2, then what happened? Here del P2 and this P2 will get cancelled and this integral will get removed. So here del C by del P2 I equals to 1 to K lambda I, and this differential of this is what? Del Fi by del P2, and differentiation of del P2 is what? 1. So only delta 2 is left. So only delta 2, which is equals to 0. Equation is seen to be identical to the principle of virtual forces, in which virtual force delta F and delta P acts through real displacement lambda. Right? And from which what we can say here, this delta 2 will be equals to this one, right? So first what we have to do, we have to find delta 2. How? First find the total complementary energy method, right? Total complementary energy, and then at what point we have to find that also, and then with respect to, because at that point we are applying the virtual force or fictitious force, so differentiate with that fictitious force. So after differentiating the fictitious force, we got delta 2 equals to this one. Okay. So what will be the lambda I, that extension, that is earlier in mechanics of solid also you had seen lambda equals to FL upon AI, where F is the force acting, L is the length of the member, and AI means A is the cross-sectional area of the member, EI is the Young's modulus of that member. If suppose same material is there throughout, means all the members are of same material, then no need to write EI. Simply that will be E, and that you can take common in the previous, in this equation. Right. If having the same cross section, then also AI will be A for all. Then also we can take for this one, or just I am writing here this equation. Let me see, here it is there. No. Okay. So let's see here. So lambda is what? Fi Li by AE. Right? When each member, all members are of same E. Same cross section and same E, Young's modulus of elasticity, means same material or same material, right? Then this AE we can take common, right? So simply we can write instead of this 1 by AE sigma, okay, Fi Li into del Fi by del P2, that we can write. If cross section is different for different member, then again in terms of AI we have to write, means for lambda 1, that will be F1 L1, force in first member into length of first member divided by cross section area of the first member into Young's modulus elasticity of the first member. So if it is common, then in terms of this you can write, or if each member having the different materials and different cross section, then you can find this one. If length is also same, then again this also you can take common, right? Then Fi only will be there, means F1 plus F2 plus F3, so on, depending upon the given condition. So that's why I just derived here with the normal condition. If it's given any particular condition is there, right, that you can use. Yeah. Okay. Just here, where Li, Ai and EI are the length, cross-sectional area and modulus of elasticity, or hence modulus of elasticity of the ith member. Means for first member, Li will be L1, AI will be A1, EI will be E1, right? Similarly, L2, A2, E2, L3, A3, E3, so on, depending upon how many members are there. On the other hand, if the load displacement relationship is of a non-linear form, so here, up to this what we had seen, that is for the linear one. Earlier it was mentioned for a linear elasticity, this here, for linear elasticity. If it is not linear elasticity, then what happens? Okay, non-linear form. Say Fi equals to B lambda I power C. That earlier we had seen for the derivation of complementary energy method, right? That P equals to B y to the power n. So similarly here P is what? F. F equals to B, instead of y was deflection or extension, so lambda I power, here they just instead of n, C. It's the same. So from here what we can say, we can find lambda I. So this is for non-linear, because this is derived for linear only. We cannot use this lambda as non-linear. So we have to replace this lambda in terms of the forces. So what we have, Fi equals to B into lambda I power C. So from here we can write Fi by B equals to lambda I power C, or Fi by B power 1 by C equals to lambda I. So that we can replace here is lambda, right? So this here Fi by B, so this is lambda I into del Fi by del P2. Okay, that is here in terms of if that is non-linear. If it is linear, then C will be equals to 1. Okay, and then similarly Fi will be B. B is what? Here, this will be B into lambda I. So B will be these things. So Fi is equals to what? Lambda I AI EI by Li. So this part is only B. Okay, and lambda I if that is linear. But if it is not linear, then we cannot use this lambda formula, because earlier in mechanics of solid also you had seen this is for the linear elastic material only, not for non-linear. For non-linear, okay, that we have to use this formula for delta 2. Okay, now just see the how to solve this member. So before that, earlier also I think I discussed this point to remember, right? So here just like forces are acting. Okay, so now how many forces? At this point force is acting, at this point force is acting, here also force is there, here also force is there, force is not here, right? And here also not there, but here reaction will be there, right? So what we will do, first we have to find the forces in each member, in this member, this member, this member. So first, if directly they give in length, then it's okay, otherwise we have to find the length of each member. So you should know length of each member, then by joint method or section method. So we will see by the one method only, because that is not in the syllabus, but still to find, we will see how to find by the joint method. So by using joint method, we will find forces on each member. Once we have the forces in each member, we can find lambda, that extension in each member, and then we can substitute in that formula and we will find the deflection. So now just see what will be the question in that one. Suppose here, find the deflection at C. So just see, at this point load is not there. Means what we have to do, we have to apply a load, that fixous load, and later we will differentiate with respect to that one. So just see here, we know that the support reactions do not appear in equation, right? So support reaction do not appear in this one, right? But we have to find that support reaction to find what? Forces in each member. Okay, so depending upon how much load is acting, based on that we will find the support reaction, and based on support reaction only we will find load in each member. This convenient absence derives from the fact that the displacement delta 1, delta 2, delta 3, so on, delta n are the real displacement of the frame. So because of that, whatever is there. The complementary energy of the reaction at A and the vertical reaction at B is therefore 0. So just here, the complementary energy at this point, because there is no displacement. So what? No displacement means no energy will be there. No complementary energy as the point is 0. Since both of their corresponding displacement is 0, because those 2 points will not have any displacement. So the complementary energy of those 2 points is 0. Okay. If we examine equation A, that earlier, we note that lambda I is the extension of the ith member of the framework due to the applied load P1, P2. Lambda I already we had seen that lambda I we have to find. Therefore, the load Fi in the substitution for lambda I in equation A are those corresponding to the load P1. So because of P1, whatever Fi is there, that lambda I is what? Fi by Fi into Li by Ai into Ei, that we have to find. Now after finding that, because of what load we are finding, because of P2, so just differentiate the term del Fi by del P2 in equation A represent the rate of change of Fi with P2 at point 2. At point 1 means point 1 also we can take. So suppose at this point we have to find, that time you have to differentiate with PC. Then why? Because what a virtual load you will apply here. If suppose you are applying virtual load at point C as PC, then you have to differentiate with respect to PC. If you are applying P1 at C, then you have to differentiate with P1 at C. So whatever the virtual load you will apply, that you have to differentiate with that one. Okay, so just here, because we are taking it as 2, so that P2. Okay, and is calculated by applying load P2 to the unloaded frame and determining the corresponding member load in the P2. Same as usual method, just remove all the loads, apply the fixed load, find that one, or apply the virtual load. So virtual load at this point. Okay, next, this procedure indicates a method for obtaining the displacement of either a point on the frame in a direction not coincident with the line of action of load. So just here, the procedure indicates a method for obtaining the displacement obtaining the displacement of either a point of that point, how it's getting displaced on the frame in a direction not coincident with the action of load. So, like suppose load is acting in this one, so in this direction it should not coincident with the deflection. That deflection should not coincident. Then we can find that one. Okay, a point such as C which carries no load at all. So at C there is no load, means there is no coincidence with the load. So we can find the deflection. We place at the point and in the required direction a fixed or dummy load PF. So here, right, PF or PC, whatever you can. At point C you are putting, then PCF also you can write, means one for virtual force or fixed force you have to apply there. The original load being removed. Then remove the original load. Now find because of the virtual load. The load in the member due to PF are then calculated, and dF by dou PF, del PF by del F by del PF obtained for each member. So now after removing all the forces, find del F by del PF. Okay, substituting in deflection equation, that is equation A, produce the required deflection. Right, we will see in the numerical how to find by tabular method. It will be easy. So first we will write the name of the member, then length of the member, then we will find the force by using the point joint method, right, that load. Then after remove, because first we have to find forces in each member, and then what we have to do, we have to, in next step we have to remove that forces, and then we have to find forces because of that PF. Okay. Okay. It must be pointed out that it is not absolutely necessary to remove the actual load during application of PF. So it's not necessary. If it is there, that by that method also we can find if that load is acting. If that their load is not there, then we have to apply the fixed load. So it's not necessary always at what point we have to find, we have to apply the fixed load only, or we have to remove the actual loads. If at that point it is there, then we have. So if already that force is there, then no need to add the fixed load. The force in each member would then be calculated in terms of the actual loading and PF. So then now find in terms of what? Actual load and PF. Fi follows by substituting PF equals to 0, because PF we applied the virtual load. So now put PF equals to 0, and del Fi by del PF is found by differentiation with respect to PF. Now differentiate del Fi with respect to that virtual forces, that is del PF. Obviously the two approaches yields the same expression for Fi and del Fi by del PF, though the latter is arithmetically clumsier, but this method is what? Arithmetically it's clumsier. How that is there? That we will see in the numericals. Okay, so make sure to remember these points. That's why I just mentioned here the points to remember. If you will remember these points, then only you can solve this type of method, because this method will be very lengthy. Even it will take, even you can see in one full video we will solve one numericals only, and that also video will be long. Why? Because see again, first they will give some this type of diagram, that is structural loading. They may give 1, 2, 3 or any number of loads. Suppose if 2 loads, 3 loads are there. Okay, then what we have to do here, the first thing, because of that load we have to find the support reaction. That support reaction, though, that is no deflection, means strain energy won't be there, but support reaction will be there, right? You cannot say support reaction won't be there. Because of the support they will produce the reaction. Because of that only the structure is stable or in equilibrium. So first you have to find this reactions, that Ra and Rb. After finding that one, we will see how to find the load in each member. So by joint method we will find load in each member, right? All the members we will find the loads first, right? So then next, at what point we have to find the deflection? At, suppose at given at C, then at C we will apply the deflection by removing all the acting forces. We will remove this one, this. We will apply one fixed load C. Now because of this C, we will find deflection in all the members. Okay, so we will find deflection in all the members, and then just what next, we will differentiate with respect to this fixed force. Then we will get Fi, dou Fi by del Pfi, and then we will directly substitute in the equation. So this equation, it will take, even after practice also, it will take minimum 15 to 20 minutes, but you have to practice a lot, then only in 15-20 minutes you can solve this equation, because depending upon how many members are there, that many times you have to find length force, then frictional force, differentiate, then multiply, then you have to find the lambda, right? So depending upon that, you have to practice a lot for this type of numericals. Okay, so make sure to remember all these points. Okay, I'll just quickly see this one. Okay, that already we discussed. So again, you can refer this book that TSG mentioned, aircraft structure, that is your textbook. Okay, you can refer with that one. That edition can be of any one, that is not necessary. This or edition only you can follow. I am following this edition, that's why I just mentioned this one, right? So if you have any doubt or anything, you can just comment on the video, or you can just contact me regarding your doubts. I will clarify. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.